Fractions. It's the most common topic cited by those who have grown to dislike math, cited as the moment in which they began to realize that they were going to struggle with this. And perhaps after watching the video that I just showed you, it's an animation I made a few years ago, it can perhaps become somewhat apparent as to why. Fractions are unusual things. They're made up of two numbers, and yet they represent a single quantity, and not just a quantity, but also an operation, a division of one number by the other. And so in that sense, they're very abstract concepts in their own way. And according to educational psychologist Piaget, abstract concepts, the ability to absorb and understand abstract concepts, wakes up at a different time for every student growing up. Actually, one of my theories on why some people don't like math is that they just happen to be a late bloomer when it comes to the waking up of abstract thinking concepts at the time in which things like fractions and pre-algebra and algebra were being presented to them. But now that we're all adults and we can look at this with fresh new eyes, perhaps we can do that and see these things for the wondrous things that they actually are. Ways in which we can further represent algebraic, quantitative patterns and relationships in nature. They're very useful. Let's take a moment to, first of all, do some warm-ups. This reaches back into our previous video in which it asks you to do two things that we discussed last time. Number one is to simplify or evaluate the expression up there, keeping in mind what's the center of the onion. What is your order of operations that you want to be following in evaluating that? Secondly, we've got a problem with a parallelogram in it, in which I'm asking you to find not only the area of the parallelogram, but also the perimeter of it. Take a moment to work on those. Welcome back. Well, hopefully those two problems were fairly straightforward when it comes to how to solve them. The center of the onion in the first problem was definitely the operation -15 plus +10 sitting inside of those small parentheses inside of there, nested inside some larger square brackets, which were actually the second step, the first layer around the center of the onion. And hopefully it was pretty straightforward, finding the area of the parallelogram with a base of 11 feet and the height of 5 feet. You use those two quantities, multiply them together to give you the area, 55 square feet. And having a base of 11, also a top of 11 if the base is 11, and two sides on opposite sides being 7 feet, that adds up to a total of 36 feet for the perimeter. Hopefully that was straightforward. If not, go back into your notes from last time and refresh your memory from what we were discussing in the previous video. Let's now take some moment to center ourselves, to make it so that We are emptying our mind of extraneous thoughts from things going on outside of our time together. So let's take a minute to do that, please. In our study of fractions, we begin with understanding that there are two different kinds of numbers that we work with. Actually, three different kinds of numbers, because there are two numbers that don't fit into either category. We touched on this a little bit last time as we were creating prime factorization trees. We have numbers that are prime and numbers that are not prime. Those numbers that are not prime we call composite. A good way to understand prime numbers is to think of sodas in a grocery store. Sodas are usually presented in 6-packs or 4-packs or 8-packs, and there's a reason for that, and that is that you can usually store them in 2 rows of 4, or 2 rows of 3, 2 rows of 2, perhaps even 3 rows of 3. You can have 9 sodas as well. 4, 6, 8, 9 packages of all of those things can be placed into more than one row, because 4, 6, 8, and 9, all of those are composite numbers. None of them are prime numbers. A good way to think of a prime number is that the only way in which you could store a set of sodas of that number, say 5 sodas, is to place them in a single file line on end, a single row. And if you tried to put them in 2 rows of 3, well, you'd have a vacancy in one area and you'd be wasting space. So the only way in which you could effectively store them is in a single row. That's true for 3 sodas. It's true for 2 sodas, actually. 2 is considered prime. It's the only even prime number. That's true for 5 sodas, 7 sodas, 11 sodas, 13 sodas. I have this silly picture in my head of somebody taking a row of 13 sodas outside of the store. It'd be fairly awkward to do. But that's a good way of thinking of what exactly a prime number is. It's a number that you can only be divided by 1 and itself. You can't place it in a certain row, a row of 2 or 3 or 4, because there's no way to divide it evenly by 2 or 3 or 4 or any other number. So here's an example of this. 19 is a prime number. The only factors of 19 are 1 and itself, 1 and 19. 51, however, is a composite number. If you had to give somebody a package of 51 sodas, you could actually place them in 3 rows of 17. I don't know why you'd ever want to do that, but you could if you wanted to. So 51 is not a prime number, it's a composite number. There are 2 numbers that fall into neither category. Those numbers are 0 and 1. Those numbers are considered neither prime nor composite. It's the only exception to the rule. So take a moment to identify whether or not these 3 numbers are prime, composite, or neither. Take about 30 seconds for that. Welcome back. As you can see from what's shown up here, 39 can be divided into 3 rows of 13, 3 times 13. 0 is, of course, neither prime nor composite. 41, turns out, is prime. Here are some perhaps familiar diagrams when it comes to learning fractions. In the top figure there, we have a pizza or a pie or a cake or something that's been divided into 5 slices, 5 quantities, and you can see that we are selecting specifically 2 of those in blue. And so the way we describe this fraction is simply 2/5. Or as in a more general sense, it is the portions that are shaded, or the portions that we're dealing with, divided by the total portions, the numerator and the denominator. Similarly, below, we're working with triangles. We can divide something up no matter what shape it is. It doesn't have to be a circle. As you can see, this is a triangle, and it's being divided up into a set of smaller triangular pieces. That's okay, just as so long as each one of those pieces is exactly the same size. As you can see, perhaps by counting them up, there are 9 of them, and 3 of them are shaded blue. So this is a way of describing 3/9. So take a moment to look at these particular figures and write down the fractions which they describe. Take a moment to do that, please. Welcome back. In particular, the third one of these looks rather strange and unusual. But it is an acceptable way to divide that triangle up into equal slices, equal triangles. But it's pretty cool that that's a way in which you can divide it up into 8 smaller triangles, of which 5 are being shaded in. Here are some properties of fractions that we want to review and discuss, perhaps for the first time, perhaps as a review. Here's one thing to keep in mind. When we have a 1 in the denominator, we're not dealing with halves or thirds or fourths. We're not dividing the whole pie up at all. This is 8 whole pies, or simply just 8 pies. This is an instance where anything that has a 1 in the denominator is simply whatever it is on top. And a good way of describing that algebraically is to use letters instead of numbers. So whenever we have a fraction that has a 1 in the denominator, that's the same thing as whatever it is in the numerator on top, simply being that whole number. A good way of writing 2 as a whole number is simply 2 over 1 as a fraction. 5 as a whole number is simply 5 over 1 as a fraction. And what we're seeing here is, in algebraic language involving the letter A way of summarizing that rule, which is always true. Always, always, always. Another one. If we have a 0 in the numerator, how many items in that figure that you saw previously are being shaded? Well, the answer is 0, none of which is being shaded. The size of the quantity being described there is simply nothing, simply 0. So a good rule to understand here is that whenever you have a 0 in the numerator, no matter what you have in the denominator, the quantity is simply 0. We can simplify that fraction to simply 0. Similarly, if we have a 0 not in the numerator but in the denominator, what we just list that as is actually undefined. It's something that doesn't really make any sense. How many times does 0 go into 2? Well, That's not really a valid question, or it seems somewhat incredulous. And so another rule that we have is that whenever you have a 0 in the denominator, if you've got something in the numerator, you can ignore that. Essentially what it is it's undefined. Something else to keep in mind. We haven't discussed this yet so much, but we'll be talking about it later on. You perhaps have heard that a negative times a negative equals a positive. It is also true that a negative divided by a negative equals a positive as well. But so we can see that a little bit here, where a -3 divided by a -3 is actually equal to a positive number. But more to the point here, you can see that -3 over -3, whenever you have the same number, top and bottom, numerator and denominator, same number, you can simplify that fraction to simply being 1. Think about this. 2 halves, 4 fourths, 6 sixths. Think of those in terms of pies. Think of those in terms of cups of sugar. Two halves of a cup of sugar is simply 1 cup of sugar. Think of this in terms of a ruler. 4 fourths of an inch is simply 1 inch. So whenever you have the same number, top and bottom, on a fraction, you can simply rewrite that fraction as the number 1. You can see that symbolized here with a over a. No matter what a is, if it's the same thing, top and bottom, we can simplify it to 1. Now let's talk a little bit more about a negative divided by a negative being equal to a positive. You can see that here with -3 divided by -4. Well, as it turns out, that's a positive number. Another way of thinking of it is that you can actually cancel those two negative signs, top and bottom, leaving you with simply 3 fourths. And so a way in which we might write this in terms of algebraic language, if we have a negative a divided by a negative b, those two negative signs can simply be canceled away, so that the fraction can be rewritten in a more simplistic form, simply a over b. Lastly, if we have a negative sign sitting out front of a fraction, that's also the same thing as having a negative sign specifically in the top of the fraction divided by a positive number. It's also the same thing as having a positive number on top divided by a negative number in the denominator. So a good way to think of it is that if you have a negative number in the top and it's a positive in the bottom, you can move that negative sign from top to bottom. You can even pull it outside of the fraction as a way of describing it as a negative quantity. So we can see that represented here in algebraic language. A negative a over b is the same thing as negative a over positive b. It's the same thing as positive a over negative b. You can move that negative sign around the fraction and you're still dealing with the same quantity. So take a moment to write those properties of fractions down. Make sure that you have those sitting on your activity sheets. Take a moment to do that, please. Welcome back. We can also categorize fractions in the same way that we categorize numbers as being prime or composite or neither. As it turns out, there are two different kinds of fractions here, and I'm showing you two examples of the first kind. You can see the first one there is simply 2/5. The second one is 4/5. These things are called proper fractions, and you'll see why in a moment when I show you improper fractions. A good example of an improper fraction would be 5/5. Another good example would be this fraction, which is 8/5, 8 over 5. So think to yourself, what's the pattern here? What defines something as being an improper fraction over a proper fraction? Well, perhaps you're seeing here that what defines an improper fraction is that the numerator is the same or greater than the denominator. All of the fractions shown with blue pentagons are improper fractions. The number in the numerator is greater than that of the denominator. That's not the case with the proper fractions shown with red pentagons. So here's a few examples here. 12/5, well, that's improper. The 12 on top is larger than 5. 5/12 is proper since the numerator is smaller than the denominator. 12/12, also improper. Improper exists even when the top and bottom are the same. And perhaps you remember from our previous discussion, anytime you have the same number, top and bottom, you can actually simplify that fraction to simply the number 1. So take a moment to categorize these fractions as being either proper or improper. Welcome back. As you can see, the first fraction is proper, the second two are improper for reasons in which we've already discussed. Let's talk about some of these improper fractions because they pop up every now and then when we're dealing with quantities that are greater than 1. Here's an example here. The length of this screw is more than 1 inch. As it turns out, those smaller lines describe 1/16 of an inch. There are 16 of those from 0 to 1 inch. So as we're taking a look at where the end of that screw is, that point comes down to about 3 additional delineations of 1/16. So this is actually 16, 17, 18, 19/16 of an inch. That's an improper fraction, but it's a way of describing the length of that screw. You can also see it in terms of the sections of pi shown in the second part here, where we have 2 holes, each one of them being divided into eighths, so that's 8/8. Another 8/8 would be 16/8. There's 3 more there, 17, 18, 19/8. Once again, 19/8 can be shown using multiple pizzas in this case. So take a moment to write some improper fractions for the screw, the length of the screw on top, as well as those pizza pies listed below. Welcome back. You can see that the screw there extends 1, 2, 3, 4, 5, 6, 7 additional 16th marks out from the number 1. That's 23/16. And on the bottom we have 8/8 plus another 3/8. That's 11/8. Let's talk about mixed numbers. It's another way of describing quantities that are greater than 1. In this case, you can see that we're dealing here with halves, but we can also describe this in terms of 3 wholes plus 1/2. So 3½ is actually the same thing as 7/2. You can see that here by how you can convert from one to the other by saying that there are one pair of halves for each one of those wholes. So 2, 4, 6 plus one additional one. And so hopefully I'm trying to show here with some colors in the lower section of the screen how you can go immediately from a mixed number like 3½ to an improper fraction. We have to use both mixed numbers and improper fractions in mathematics. It's easier to do calculations when you're doing improper fractions. However, if you're going to some cooking department or a trip to Home Depot, you're going to find a lot more mixed numbers there than you will find improper fractions. So we need to be able to use both and convert from one to the other. And you can see here that this is the way in which we would convert from a mixed number, 3½ to an improper fraction, 7/2. So let's do the same thing here, converting the mixed numbers to improper fractions. 7 1/4. Okay, so we're dealing here in fourths. How many fourths are in the first whole pie? Well, there's 4 of them. There's another 4 in the second one, another 4 in the third one, fourth one, fifth one, sixth one, and seventh one. So there's a total of 7 times 4 of those fourths. That's 28, plus one more for 7 1/4. A total of 29 fourths. So you can see the calculation that we had to go through there. 7 times 4 plus 1, 29 fourths. We can repeat the same thing with the bottom one here. Just keep the negative sign out front. Don't worry about the fact that there's a negative sign there. We can still convert that mixed number into a fraction by multiplying 8 times 5 and then adding 2. This is negative 42 fifths. So take a moment to convert those mixed numbers to improper fractions. Take a moment to do that now. Welcome back. You can see a repeat here of the calculations that we did in the previous slide here. 10 times 8 plus 5 is 85/8, and 15 times 2 plus 1, 31/2. Actually negative 31/2, isn't it? Well, we've converted from mixed numbers to improper fractions. Now let's convert back. Let's convert improper fractions back to mixed numbers. Well, how in the world do we convert 13 fifths, shown with this illustration in the form of pies divided into fifths? Well, we have 13 of them there. And how in the world do we do this? Well, perhaps one way is to draw a picture like this. You could do it this way, and it would be a fine way to do it, but it might become a little tedious and tiresome as time goes on. An easier way to do this is to remember a concept that was introduced in the previous video, the animation video that I had you watch, and that is that fractions are division. When we're dealing with 13 fifths, we are showing the result of 13 divided by 5. And we can find out what that answer is as a mixed number by simply doing 13 divided by 5. You can see that illustrated just above my head here. 13 divided by 5. Remember, 13 is going to go inside the box. The number on the top goes inside the box. Always, always, always. 13 divided by 5, well, we first ask, how many times does 5 go into 13? Well, it goes twice. 2 times 5 is 10. We subtract 10 off. We have 3 left over. The answer is 2 with a remainder of 3. How in the world do we use that information to create our mixed number? Well, perhaps the clue can be found in the illustration here. 2 with a remainder of 3. What's our mixed number going to be? Well, hopefully you can see here that we're still going to be working in fifths, but the 2 is going to be our whole number sitting out front, and the 3 is going to be the number sitting in the numerator. That's how we construct our mixed number. 13 fifths is 2 3/5. So let's do this with a few more examples here. 25/6, okay? Well, for this, we divide 25 by 6. Remember, the number on top goes inside the box. 25 divided by 6, well, 6 goes into 25. 4 times, we subtract off 24 with a remainder of 1. And so our answer should be 4 1/6. In the same way, we have a negative sign out front. We can ignore that for a moment. 39 fourths, well, once again, we're taking 39 and we're dividing it by 4. 4 goes into 39 9 times. We subtract off 36 to get a remainder of 3. What is our mixed number going to be? Remember, it's still negative. 9 3/4. So take a moment to do this for these two improper fractions. Take a moment to do that now. Welcome back. Well, hopefully that gave you a chance to exercise these new skills in a way that worked out fairly well for you. If it didn't, feel free to rewind the video a little bit and go back to learning some of these concepts once again. As I said before, fractions are division. And so as we're working with fractions, we're working with division problems. Another way of writing 529 25ths is 529 divided by, using that old division symbol that we remember, 529 divided by 25. So we can approach this kind of problem in the exact same way and get a mixed number as our answer. 529 divided by 25. Remember, the first number would be the top number in the fraction here. So 529 goes inside the box. So 25 goes into 529. Well, 25 into 52 twice. We subtract off 50. We have 2 left over. We bring down the 9. 25 goes into 29 once. We subtract off 25. We have a remainder of 4. So predict what the mixed number is going to be. Hopefully you were correct there. 21 4/25. So do this on your own as well here. 5,967 divided by 41. Take a moment to do that, please. Welcome back. Our journey into fractions allows us a chance to reinforce our long division skills as we divide 5,967 by 41 to get 145 and 22 41sts. 22 41sts there. So that remainder of 22 becomes the fraction part of the mixed number. Let's also talk about fractions in terms of the number line, or in terms of a ruler. I've already shown you an example of a ruler when we were measuring the length of a screw. But in this case, I'm showing you a number line with the number 0, as well as the number 1, kind of above my head here. And there are a series of lines of equal distance going from 0 to 1. How many of them are there? 1, 2, 3, 4, 5, 6, 7, 8. So each one of those lines represents an eighth going from 0 to 1. So where on this number line will we place a half? Well, think in terms also of what's the line that is half the distance between 0 and 1. Well, hopefully you can see that there is a line there in the center that would, that even though it's measuring in terms of eighths, is actually half the distance from 0 to 1. And it's right there. Similarly, 3/4, that's half the distance between 1/2 and 1 whole. And so you can see that that's a place where you could mark it off right there. 11/8. Well, we know that each one of those lines is an eighth. 8/8 would be 1, so an additional 3 lines, 1, 2, 3, would be 11/8. Let's reinforce these same skills on our own as we plot 7/8, 3/8, and 5/4 on the line given to you there. Welcome back. Well, hopefully that was fairly straightforward. You were dealing with eighths on the first 2 of the 3 fractions. And the last one, 5/4, well, you'd have to think in terms of how much is a fourth if you're dealing with eighths here. It's actually 2 of those lines being equal to a fourth, and so you'd have to extend it out another 2 lines from 1 to give you 5/4. Let's talk some more about factorizations. Let's find 3 different factorizations of a number. For the number 12, it can be divided up into 2 times 6, into 3 times 4. It also can be divided up into 3 times 2 times 2. That's the unique factorization when we're dealing with just prime numbers. So let's actually take a moment to do that for 18 as well. What are 3 ways in which we can multiply whole numbers together to get 18? Think of that for a moment. Welcome back. One thing that I didn't mention that I should mention is that you might have listed as one of your factorizations of 18 as 1 times 18. That's technically true, but it's one that we want to avoid just because we want to split the number down into specifically smaller numbers so that we don't include 18 any longer. As you can see, there are 3 possibilities that I'm showing here: 2 times 9, 6 times 3, and 2 times 3 times 3, the one involving exclusively prime numbers. Let's do this same kind of thing as a prime factorization. Now, I introduced this a little bit in my previous video. Let's reinforce it all the more here. What are 2 numbers that can be multiplied together to give us 220? What are some factors of 220? Well, 22 times 10 is a good way of doing it. 22, let's ask the same thing for 22. What are 2 numbers that can be multiplied together to give us 22? 11 times 2 comes to mind. Let's do the same thing for 10. What 2 numbers can be multiplied together to give us 10? And the answer would be 2 times 5. Now notice with each one of these numbers on the bottom, all 4 of those numbers are prime. 11, 2, 2, and 5. We've gone as far as we can as far as factoring this number completely to prime numbers. And so a good way of describing a prime factorization of this is to list the ends of the tree, so to speak, the ends of the fingers. 2 times 2 times 5 times 11. Notice I always stick them in order from smallest to greatest. That tends to help things out as well as being organized. So do the same thing here, but with the number 90. Find the prime factorization of 90. Do that now. Welcome back. Now you might have chosen a slightly different path than I did with my factorization tree here. Instead of 9 times 10, maybe you chose 45 times 2. Maybe you chose 15 times 6. There's a lot of ways to do it, but you should be getting to the same prime factorization combination that I've got sitting above my head here. 2 times 3 times 3 times 5. That should be unique, even though there are multiple ways to get to it. Let's do some more practice for prime factorizations here. Let's take 198 and let's split it into 18 times 11. 11 is prime, and so we'll leave that one alone, but 18 is not. We can split that into 9 times 2. We could also split it into 6 times 3. Then let's split 9, once again, into 3 times 3. Nothing else can be split. And so we're looking specifically at the ends of the tree, the ends of the fingers, and if we put those into numerical order, we have the prime factorization of 198. 2 times 3 times 3 times 11. Let's do one more, 153. As it turns out, that can be factored into 9 times 17 or 3 times 51. There's a lot of different ways to do it, but we will get to the same answer no matter which way you're going. 17 is prime, so we'll leave it there, but 9 can be split into 3 times 3. And that gives us our prime factorization for 153, which is 3 times 3 times 17. So here's a chance for some more practice here, the prime factorization of 168. Welcome back. Now it's okay if your prime factorization tree on the left looks different than the one that I'm showing. There are multiple ways to get to this answer, but your answer should still be identical to the one that's showing above my head here. 2 times 2 times 3 times 7. There's a lot of ways to get to the same right answer. Here's one more. Let's do the prime factorization of 990. Welcome back. This problem is a little harder than the previous one. It's also a good example of making sure that you only focus on the ends of your fingers, the ends of the tree branches there. So it's a little bit hard to tally up all 5 of them there into our prime factorization of 990, which is 2 times 3 times 3 times 5 times 11. Let's talk more about fractions. I'm showing you here 4 different representations of a half of a pizza here. You're seeing here a half of a pizza in each instance, but represented in different ways. In the first one, it looks like the pizza's only been divided into 2 slices to begin with. Perhaps these are 2 roommates sharing a pizza. In the second one, it's apparently been divided into 4ths, of which 2 of those are still left over. In the third one, the pizza has been divided into 6, of which 3 are left over. And lastly, a pizza which has been divided into 10 slices, of which 5 are still visible. What I want you to see is that each one of these fractions, although appearing different, are actually describing the same quantity. There's a name for this. We call them equivalent fractions. Equivalent fractions. Fractions that are, in fact, the same quantity. And you can perhaps see a pattern here between all of these fractions, in that if I take, for example, 1/2 and I multiply top and bottom by the number 2, then what I can get is 2 on top and 4 on the bottom. I can get an equivalent fraction of 2/4. In the same way, I can do the same thing going from 1/2 to 3/6 by multiplying top and bottom by 3, and I get 3 on top and 6 on the bottom. I can get an equivalent fraction. In the same way, going from 1/2 to 5/10, I can multiply the top and bottom by 5, giving me 5 on top and 10 on the bottom. So, the moral of the story here is that if I'm given any fraction, say 2/3, and if I multiply it by the same number, top and bottom, no matter how big and ugly that number might be, I will get, in this case, a pretty ugly looking fraction, but in fact all it is simply 2/3. A way in which we can describe this in terms of algebraic language is that if we've got any fraction, a over b, and we multiply the same quantity, the top and bottom, by the same quantity c, we'll get a fraction that's the same size as the original fraction. We'll get an equivalent fraction. Multiplying top and bottom by the same number c does not change the quantity represented by the fraction. Another way in which we can check to see if 2 fractions are the same size is to do something called cross products. And that is that if 8/10 is equal to 4/5, as we see in this top one here, if that is true, then if I multiply these 2 numbers that I'm showing here with the green oval, I should get the same number as when I multiply these 2 numbers shown by the blue oval. In other words, 8 times 5 should give me the same answer as 4 times 10. Well, both of them give the answer of 40, so we've confirmed that these two fractions are in fact the same. We can see another example of this in the lower portion, 9/12 being equal to 3/4. Well, maybe we're not sure about that. Let's confirm that. 9 times 4, well, that's 36. 3 times 12, also 36. So once again, we've confirmed that those two fractions are equivalent, describing the same quantity. So a good way to describe this in terms of algebraic language is to say that if one fraction, a over b, is equal to another fraction, c over d, then the cross products between those two should also be the same. What does that mean? Well, it means that AD should be the same as BC. A times D should give me the same quantity as B times C. This is a way of describing with algebraic language something that's always true, a pattern, a relationship that is always true. Again, this is the joy of algebra. So do this. Well, we'll do it together here. Determine if the following fractions are really equal. You notice I've placed a question mark above that equal sign because I'm not sure if that's true. So let's find out. 5 times 24, maybe that's the same thing as 8 times 15. Maybe it isn't. 5 times 24 is 120. That's also what we get when we multiply 8 and 15. So the answer is yes, those two are equivalent fractions. So do this one on your own. Is 6/9 the same thing as 10/15? Welcome back. By discovering that 6 times 15 gives us the same answer of 9 times 10, which is 90, we find that those two fractions are indeed equivalent to each other. Here's another one. Is 9/12 equivalent to 12/18? Take a moment to determine that. Welcome back. For the first time, we're getting an answer of no when it comes to two fractions being equivalent. 162 is not equal to 144. The cross product fails. So we've seen two ways so far in which we can work with equivalent fractions. We've seen that we can do cross products to see if two fractions are equal. We found also that if we multiply top and bottom by the same quantity, we can get an equivalent fraction. Now, in addition to multiplying top and bottom by the same quantity, we can also factor top and bottom by the same quantity, or another way of saying it, divide by the same quantity top and bottom. You can see that 11/33 we're factoring into 1 times 11 over 3 times 11. And what that gives us is 2 11s that we can cancel out, so the fraction is essentially just 1/3. So in this case, there's a common factor of 11. In fact, it's the greatest common factor between 11 and 13 that we can factor out and cancel top and bottom in going from a fraction that is more complex to one that is more simplified. So you can see here our concepts of greatest common factor are starting to pop up as we're dealing with fractions. Now this can be a little bit challenging because you can sometimes be presented with a fraction that is so complex that it can be a little bit challenging trying to figure out what things you can divide top and bottom, or what things you can factor out of top and bottom in order to simplify the fraction. But here are some things you can do to try and do it piece by piece. One thing that comes to mind is 2 a factor of both 84 and 126? Well, they're both even, and so the answer to that is yes. So 2 is a common factor from top and bottom. In addition to this, there's also something else that is useful. 8 plus 4 of the 84 on top, 8 plus 4 equals 12, and 12 is divisible by 3. That means that 84 is in fact divisible by 3. And on the bottom, 1 plus 2 plus 6, those digits of 126 add up to 9. 9 is also divisible by 3, and so 126 is also divisible by 3. That's a special rule, only works for 3's, but it's very, very useful in this context here. So 3 is also a possibility. Not just a possibility, one that we can actually utilize in factoring these 2 numbers, top and bottom. And so let's take this one step at a time here. 84 can be described as 2 times 42. So think of it as building a factorization tree going upwards here. And from 126, we can factor that out into 2 times 63. We have a common factor, top and bottom, of 2. Those can be canceled out so that we now have 42 divided by 63, 42 63rds. On top, we can factor a 3 as we knew we would be able to. 3 times 14 is equal to 42. In the same way, 63 can be factored into 3 times 21, and so we have 3's top and bottom, common factors that can be canceled. What's left is 14 over 21, and perhaps you can recognize those 2 numbers as both being divisible by 7, 14 being 2 times 7, and 21 being 3 times 7. So we again have 7 as a common factor that can be canceled out, top and bottom, so that we have an answer of 2/3. And so we're able to do this step by first factoring out 2, then factoring out 3, then factoring out 7. Now something to keep in mind here is that this actually means that the greatest common factor of 84 and 126 is actually not 2, not 3, not 7, but 2 times 3 times 7, or in fact 42. So in fact, if you, for some strange reason, knew that 42 went into 84 and also went into 126 evenly, then you could factor that out quickly and do all of this in simply one step, since 42 is the greatest common factor of those 2 numbers. For me, it's just easiest to simply do this in a series of steps, just knowing your 2's and 3's and 5's and things like that. And so let's actually review some of these rules for divisibility here. Perhaps I should have discussed this a little bit earlier when we were doing some of our prime factorization trees, but let's cover it now. For 2, divisibility by 2, we're simply asking whether or not the number is even. And we all know that that's done by looking exclusively at the last digit. If the last digit is 0, 2, 4, 6, or 8, we know that the number is even and it's divisible by 2. We've already discussed that divisibility by 3 is shown when the digits actually add up to a number that is also divisible by 3. So that's an easy way to figure out whether or not something is divisible by 3. For 4, it's a little bit more difficult, but it's important to note that when you're figuring out if a number is divisible by 4, you only have to look at the latter 2 digits and ask if those 2 digits form a number that is divisible by 4. What does that mean? It means that if you're asking whether or not the number 1016 is divisible by 4, the answer is yes, because the last 2 digits are 16. And 16 is divisible by 4 Therefore, 1016 is divisible by 4. You only have to look at the last two digits. For divisibility by 5, if you count by 5s, 5, 10, 15, 20, you notice that the last digit is always either a 0 or a 5. For divisibility by 6, you simply ask whether or not the number is divisible by both 2 and 3. If that's the case, they're both divisible, then the number is divisible by 6. And lastly, divisible by 10. Anybody who's counted by tens, 10, 20, 30, 40, 50, know that divisibility by 10 is indicated by a 0 in the last digit. Simplifying fractions to lowest terms. We can use a lot of these divisibility and common factor terminologies to be able to do this. Before I do that, let's actually take a moment here to write down these rules for divisibility into your activity sheets. I'm going to give you a little bit of time to do that. All right, let's use these rules to be able to simplify some fractions down to their lowest, most simplified terms. Let's start on the top with 6/10 here. Well, what's a common factor of 6 and 10? Well, they're both even, so let's actually start there and factor out a 2 from top and bottom. 6 is equal to 2 times 3, 10 is equal to 2 times 5. We have a common factor of 2 that can be canceled, top and bottom, leaving us with just 3/5. 3 and 5 are both prime, so we know that this fraction is in its lowest terms. Let's move on to negative 170 over 102. That's an improper fraction, but we can still reduce it in the same way. We can tell, first of all, that both numbers are even, and so we can factor out a 2, again, from top and bottom. We still have that negative sign out front. We're just keeping it there. We don't have to do anything with it. But 170 is equal to 2 times 85, and 102 is equal to 2 times 51. So we can cancel those off, leaving us with negative 85 51sts. 51 is divisible by 3. 85 is not divisible by 3, since 8 plus 5 is 13. So I think that that's the point where we can stop. Oh, I'm wrong. Actually, 17 goes into both 51 and 85. It goes into 51, that's right, 3 times, and it goes into 85 5 times. And so we can once again factor out what is in fact another prime number of 17, leaving us with just negative 5/3. Lastly, 20 24ths here. Again, we're dealing with two numbers that are actually divisible by 2, actually also divisible by 4, so we could jump ahead that way. But so let's do it. Let's actually do that. 20 is equal to 4 times 5. 24 is equal to 4 times 6. Those can be canceled to give us 5/6. The fraction is once again in its lowest form. So I've given you 3 fractions here to work with to practice these skills. Have a chance to work on those at this time. Welcome back. In particular, the middle of those three problems is a little bit challenging. It's a little difficult to see that 13 is a common factor of both 26 and 195. It's certainly easier to see that with 26 than it is with 195. Sometimes you have to just try and guess and check some things in order to discover some of these more complex common factors. So here's some more practice with simplifying fractions down to lowest terms. What I'm showing you here is factoring out, noticing in this case that 25 goes into both 25 and 75. And so we can actually factor out a 25 top and bottom, leaving us with just 3 over 1 or just 3. And perhaps you saw that to begin with when you saw the fraction as a division problem. 75 divided by 25 is simply 3. Let's do the same thing with the middle problem here. 170 divided by 30. We can obviously factor out a 10 there, getting rid of the 0, so that gives us 17 thirds. And 3 being prime, I don't think there's another factor that we can cancel top and bottom here, but we can certainly convert it into a mixed number here. That's actually incorrect. That number should be 5 2/3. 5 2/3, my mistake. Let's look at the bottom one here. 2,500 divided by 75,000. Well, in this case we have not just 10 that we can cancel, a factor of 10 that we can cancel top and bottom, but actually a factor of 100 that we can cancel top and bottom, getting rid of 2 zeros at once, leaving us with just 25 and 750. We can then factor out 25 from both top and bottom, leaving us with just 1 on top and 30 on the bottom. It's pretty clear that that's in its lowest terms since the top number is just 1. Here's some more practice. Hopefully you'll do a better job than I did on the middle problem there. Take a moment to simplify those fractions into lowest terms. Welcome back. Hopefully that's some good additional practice for you that helped to reinforce some important skills. Another thing that we want to make sure that we know how to do is to order fractions. In other words, understand when a fraction is larger than another one, or smaller than another one. And the animation video that I showed you earlier gave some insight as to this, but let's also describe this in terms of more quantifiable. Let's actually describe this in other terms as well here. Now, when we have denominators that are the same, as I'm showing just above my head here, then it's easy to figure out whether or not one fraction is larger than another one. 3/5 on the left is larger than 2/5, and so we have a greater than sign extending outward towards the larger number 3/5. But what do we do on the left-hand side of the screen here when we're comparing 3/5 and 4/7? Two numbers that are different in both the numerator and the denominator. The animation talked about how it's easy when you have the same number in the denominator and you can just compare numerators. Also, if you've had the same number in the numerator, and you can just compare denominators. But what do you do when both the numerator and the denominator are different? How do you compare those two together? Well, a good way to do it is to find a way to make it so that the denominators are exactly the same. That way you have two identical denominators and it becomes easy to figure out which one's bigger, just like the one above my head. In this case, the best denominator would be 7 times 5. And so if we take, for example, 3/5 and multiply top and bottom by 7, I'm going to get 35 in the denominator, and I'm going to get 21 in the numerator. 21 35ths is the same quantity as 3/5. In the same way, if I take 4/7 and multiply top and bottom by 5, I'm going to get 35 in the denominator again, and on the top I'm going to get 20. 4/7 is the same thing as 20 35ths. And so now it becomes a little more easy to see which one is bigger. 21 35ths is bigger than 20 35ths, and so 3/5 is bigger than 4/7. So by getting the same denominator, then ordering fractions becomes a lot more straightforward. So take a moment to do this very thing on your own with this problem here. 3/8 and 4/9. Which one is bigger? Take a moment to work on that. Welcome back. I should have mentioned beforehand that the letters LCD in the upper left there indicate least common denominator. We'll talk about that more as we're talking about adding and subtracting fractions, but for now it's simply to note that we were taking 8 times 9 and multiplying those two together to give us a common denominator of 72. So we converted 3/8 into 27 72nds and 4/9 into 32 72nds. From then on it was pretty easy to see which one was larger namely 4/9. So let's get some more practice with this, where we're not only ordering just two fractions, but three fractions in which we are ranking those: -9/20, -7/15, and -4/9. Here, we're actually finding that this is a least common multiple type of operation here that we're finding. So we're using that skill in order to be able to do this here. 20 can be factored into 2 times 5 if we do a prime factorization table. 15 can be factored out into 3 times 5, and 9 can be factored out into 3 times 3. So the least common multiple is all of those factors put together, duplicates counted only once. 2 times 2 times 3 times 3 times 5, or 180. It's a large number, but it's the lowest number we can get to if we want to adequately compare each one of those fractions. Again, let's take a look at this above my head here, -9/20. Well, how do I get from 20 on the bottom to 180 in the bottom? The answer is that I have to multiply the bottom by 9. And what I do to the bottom, I have to do to the top. So the top becomes 9 times 9, or 81, and the bottom becomes 180. So that becomes -81 180ths. -7/15 goes through a similar transformation, multiplying the top and bottom by 12 to give us -84 180ths, and -4/9 gets multiplied top and bottom by 20 to give us -80 180ths. Now from here you can see that the one that initially looks like the largest one, at least, is 84 180ths. But that's actually, since this is negative, it's actually the smallest number of the three. There's a little bit of a catch here because of the fact that it's negative. How much money would you rather have in your bank account? Would you rather be $10 in the hole or just $5 in the hole? The answer is that you'd rather just be $5 in the hole, because that's the lower number. We're dealing with negative numbers, so things that are greater are actually smaller numbers. So 84 being the largest number is actually being the largest number makes it so that -84 180ths is actually our smallest fraction and goes farthest to the left over there. The one in second place is -81 180ths, and the largest one is -80 180ths. Converting back to our original fractions, that means that -7/15 is less than -9/20ths, which is less than -4/9. So let's do this on your own for a little while. Rank those fractions: -5/9, -8/15, and -3/5. Take a moment to do that. Welcome back. In this case, we were working with denominators of 9, 15, and 5, and our least common multiple of each one of those, of all three of those numbers, is 45. And so we found that we could convert negative 5/9 into negative 25 45ths. We could similarly convert negative 8/15 into negative 24 45ths, and convert negative 3/5 into negative 27 45ths. From that point, it's pretty easy to see which one is the largest, albeit somewhat counterintuitive. The largest one there is actually the smallest numerator. Negative 24 45ths is actually the largest one there, and so negative 8/15 goes farthest to the right. The smallest one there is negative 27 45ths, and so negative 3/5 goes farthest to the left, and the middle one is negative 5/9. Let's talk about how we multiply fractions. We've talked about how we convert from one equivalent fraction to another. We've talked about how we can compare fractions. We've talked about how we can convert them from mixed numbers to improper fractions and back again. We've talked about how to visualize fractions. Now let's start talking about how we manipulate two fractions together. Multiplying fractions. Here's a story I want to pose to you and ask what exactly is happening with these particular words here. I was given a slice of pizza that is 1/4 of the whole pizza. I'm showing that with the first green slice farthest to the left. I then took half of my slice and gave it to a friend. So you can visualize exactly what that would look like if I were to cut that slice in half and give that slice to a friend. What I'm actually doing there is multiplying two fractions. 1/2 of 1/4. Remember in our last video that of indicates multiplication. So half of something means 1/2 times that number. And 1/2 times 1/4, perhaps you can see it in the circle on the second one showing that actually gives me 1/8. That's how much I was giving to my friend. It's also the amount that I had left over. 1/2 times 1/4 equals 1/8. Perhaps you can also see what the pattern is in multiplying fractions there. You'll notice that across the bottom there, 2 times 4 equals 8. There's a big clue. So this was half of 1/4. Again, remember, of meaning multiplication. Simply put, here's how you multiply fractions. Take a look at this example up here. 2/3 times 4/7 equals 8/21. Take a look at that and think of how I got that. Here's another example. 3/5 times 7/10 is equal to 21/50. Perhaps you can see here that the pattern is that you multiply the numbers that are on the top to get you the number of your product, and you multiply the numbers on the bottom to get the same thing on the bottom. In this case, on top, 2 times 4 equals 8, and 3 times 7 equals 21. 3 times 7 equals 21 again, and 5 times 10 is equal to 50. Let's test that theory out with the third one here. 5/9 times 11/17 equals 55 146, and it is indeed true that 5 times 11 equals 55, and 9 times 7 equals 146. So how would you describe this using algebraic language here? If I had a over c, that fraction, a over c, and multiplied that by b over d, and a second fraction there, I would get a fraction that is a product of those two fractions. But what would be the number on the top? Well, it would be a times b, wouldn't it? And the number on the bottom would be c times d. We represent that algebraically by saying this. A over c times b over d is equal to ab over cd. This is, again, the joy of algebra, in which we can represent things that are always true, relationships and patterns, in a manner that is compact and elegant, namely what you see here. So here's an example in which you can use this in two separate problems here. Remember for the second one how you can represent a whole number as a fraction. Think about how you can do that. Take some time to work on those. Welcome back. Hopefully this was fairly straightforward. There was one thing on the bottom there in which I had you multiplying a negative number times a positive number. I haven't really gone over exactly what a negative times a positive is, but it is actually another negative. And so negative 7/12 times positive 11 firsts is negative 77/12. The negative carries through. Oh, and we can also convert that into a mixed number there, 6 and 5/12, negative 6 and 5/12. Now sometimes when we do these multiplication problems, we're left with a fraction that we can actually simplify even farther. Here's an example of this. 4/30ths times 5/14ths. Across the top, we get 20. Across the bottom, 30 times 14, we get 420. Is that a fraction that can be reduced? Absolutely. There's a 0 as the final digit on both the top and bottom, which we can factor out as a common factor of 10. We're left with 2 over 42. Both of those numbers are even, so we can factor a 2 out of both the top and bottom and cancel those 2's to give us 1/21. So you're going to run into that same kind of thing here as you're multiplying these two fractions and then simplifying your answer. Take a moment to do that. Welcome back. Hopefully that was fairly straightforward, in which you multiplied the top and bottom and realized that 4 can go into 28, it can also go into 60, so you had a common factor of 4 that could be canceled to give you 7/15. Here's another example. If we multiply these two numbers together here, and again we have a negative times a negative giving us a positive, you'll notice that I could actually as I multiplied these things across the top here, I'm actually jumping to the end where I got to 7/33. How in the world was I able to do that? Well, notice that 10 is equal to 5 times 2, and also that 18 is equal to 6 times 3. 21 is equal to 7 times 3, and 55 is equal to 5 times 11. So my question to ask is, can we cancel out common factors before doing the multiplication? As it turns out, the answer is yes. Notice that there is a 3 on top as well as a 3 on bottom. Those are two common factors that can be canceled. What are some other ones that can be canceled? Well, there's a 5 on the bottom as well as a 5 on the top. In addition to this, we also have 6 that can be factored into 2 times 3. That gives us another 2 that can be canceled off with the 2 on the top. So there's even more canceling that we can do. So what are we left with on the top and the bottom? Well, on top, we're simply left with a 7. And on the bottom, we're left with two factors remaining, 3 and 11. 3 times 11 is 33. So how in the world did I get this far, jump ahead so quickly? Simply this: you either cancel the common factors now or you cancel them later. And it's actually easier, you might notice, to do it in this early stage when the numbers are not so big. So I would encourage you, as you're multiplying fractions together, to preemptively factor out numerators and denominators into factors to see if there's something that can be canceled out top and bottom. So do these as another example here. Work on that. Welcome back. Well, this is a problem with perhaps a surprising answer, just a 1 on top. When everything gets canceled on either the top or the bottom, what's left is not a 0, but a 1. When we're canceling off factors, what's left is simply a 1. And everything got canceled off before the multiplication was done on top. And so what's left is just 1. There's one thing left over on the bottom, that's just the 5 for an answer of 1/5. Now that's how we do multiplication of fractions. Let's talk about how we do division of fractions. And in reality, it's actually fairly simplistic. It's actually just a multiplication with an additional dance step, so to speak. There's one term that has to be defined before we can go through doing division of fractions. And I'm showing you some examples of this concept called the reciprocal in the first column here. The reciprocal of 2/3 is 3/2. The reciprocal of -4/7 is -7/4. The reciprocal of 2, which can be represented, -2, which can be represented as -2/1, is -1/2, -1/2. The reciprocal of 1/3 is 3/1, or 3. With that in mind, what do you think the reciprocal of 11/12 is? I would imagine you would say that the answer is 12/11. And similarly, that the reciprocal of -1/5 would be -5/1, or -5. And that the reciprocal of 7 would be 1/7. And you'd be right. So one common thing to understand about reciprocals is that it's simply the flipping of the number. One other property of reciprocals is that if we have one fraction that's being multiplied by its own reciprocal, watch what happens here. 2/3 times 3/2. Across the top we have 6. Across the bottom we have another 6. The answer is 1. You could also see that by canceling the 2's top and bottom and canceling the 3's top and bottom, leaving just 1/1, or just 1. Same thing with the second pair of fractions. -4/7, -7/4. That gives us the same number, top and bottom, or just 1. Same thing with -2 times -1/2. That gives us 1. 1/3 times 3. That gives us 1. 11/12 times 12/11. That gives us 1. And so on and so on and so forth. So two numbers are reciprocals. Perhaps complete this sentence for me. Two numbers are reciprocals if their product is, hopefully your answer is, simply 1. And we'll actually use that when we're trying to solve equations that involve fractions. That's an important thing to keep in mind. So work on these. Very simple problems, very quick. Find the reciprocal of those 5 fractions. Welcome back. You can see here the reciprocal of 4/9 is 9/4. The reciprocal of -5/3 is -3/5. The reciprocal of -12 is -1/12. 1/4 becomes 4. And the reciprocal of 0 is undefined. Why is that again? Oh yes, it's because you cannot have a 0 in the denominator. When you flip that, it becomes not 0/1, but 1/0. There's a 0 in the denominator now, and we know from our previous discussions that that means that the value is undefined. So how in the world do we divide fractions? Well, it's important to keep in mind that taking half of something is the same thing as dividing by 2. Think about that in your own mind here. If I have a slice of cake and I'm going to divide it into I'm going to divide that cake into 2 equal slices, that's the same thing as taking half of it, isn't it? 2 ways of describing the exact same thing. So multiplying by 1/2 is the same as dividing by 2. In the same way, taking 1/3 of something, perhaps you can think of this in your mind as well, is the same thing as dividing by 3. So what's the pattern here? Dividing by a number is the same thing as multiplying by its, hopefully you can see that the answer there is reciprocal. So dividing by a number is the same thing as multiplying by its reciprocal, which means that there's only an additional dance step in converting from division problems to multiplication problems. It means that if I'm given here 5/8 divided by 2/3, I can just convert that to 5/8 times 3/2. I've taken the second fraction, only the second fraction, and always just the second fraction, and I've taken the reciprocal of that fraction. And that turns the division symbol into multiplication. From that point on, it's pretty straightforward, isn't it? We know how to multiply those two fractions, multiply the tops and bottoms to give us 15/16. In the same way, for the second problem, 11/32 divided by 3/8, we can change that to multiplication by inverting the second fraction, taking the reciprocal of 3/8 to make it 8/3. 11/32 times 8/3, well, there's actually some canceling that you can do there. 8 goes into 32. 8 is a factor of 32. 32 is equal to 8 times 4. And so there's actually an 8 that can be canceled top and bottom there, leaving us with just 11 on top and 4 times 3, or 12, on the bottom. I'll actually have some animation to show that. That's right. And then lastly, 1/2 divided by 7/12 is the same thing as 1/2 times 12/7. Again, 12 and 2 both are divisible by 2, so we have a common factor that can be canceled out, 12 being equal to 2 times 6, and so the 2's cancel, leaving behind just 6/7, or 6/7. So the only thing that's new on this slide is this extra step of converting from a division problem to a multiplication problem by taking the reciprocal of the second fraction. So take a moment to work on these as well. I'll watch the time. Welcome back. There was an awful lot of canceling that took place as we were multiplying all these fractions together that I didn't show, but hopefully it correlated strongly with what you were seeing here. For example, on the top one here, as we were taking a look at 7/8 times 16/3, there's a common factor of 8 that could be canceled between the 8 and the 16, removing the 8 and replacing the 16 with just a 2. So this became 7 times 2, or 14. And on the bottom, we simply have a 3. In the same way, there was an awful lot of canceling taking place in the second problem, the 3's being canceled out, as well as the 4 being canceled out with the 8, leaving behind just a 2 on top. So 2 over 1 being equal to 2. Here are some applications using some fraction multiplication. Here's a person who estimates that his total cost for college for 1 year is $12,600. He has financial aid that's going to be paying 2/3 of the cost. So how much money will be paid by financial aid? Well, that's 2/3 of $12,600. And we can multiply that out doing our fraction multiplication. And which means, how much money will Carson have to pay? Well, it's going to be the remaining 1/3 of that quantity. So 12,600 times 1/3. And in both cases, we can do some cancellation, top and bottom there, leaving behind just $8,400 on top and 1 on bottom. So it's going to be $8,400 covered by financial aid. A similar set of calculations takes place for the amount that Carson has to pay, giving us $4,200 that he's going to pay. Now, if Carson's parents help him by paying half of the amount not paid by financial aid, then how much money will be paid by Carson's parents? Well, the amount that Carson was paying was 12,600 times 1/3. And since the parents are going to be paying half of that, that's multiplied by another half on the end there. So we're taking fractions and multiplying them together. These are 3 fractions multiplied together. But the process is the same. We cancel out things top and bottom, and once again, things top and bottom, leaving us behind with just $2,100. So work on these here. A new school will cost $20 million to build, and the state will pay 3/5 of the cost. So how much will the state pay, and how much will the state not pay? Take some time for that. Welcome back. This problem was very, very much like the one that we did together, except the numbers that you were dealing with were far larger, in the millions of dollars, with the state paying $12 million and the state not paying the remaining $8 million. An additional part to this problem, the county school district issues bonds to pay 4/5 of the money not covered by the state. Okay, so what's the amount of money not covered by the state? That was that $20 million times 2/5. How much money will be covered by the bonds? Take a moment to work on that. Welcome back. This gave us some more practice with multiplying more than two fractions together, in this case 3 fractions. Here are some applications using fraction division. A developer subdivides 12 acres into lots, and each lot is 3/10 of an acre. How many lots are made? Well, in this case we're asking how many of those 3/10 of an acre lots go into 10 acres. That's definitely a division problem, isn't it? 10 divided by 3/10. Well, the way that we can do that is, as we recall, convert that to a multiplication problem by taking the reciprocal of the second fraction. There's nothing really that we can cancel here, top and bottom, so this simply becomes 100/3, which can be converted to a mixed number by 33 1/3. So again, our problem-solving skills, the last step is for us to take this number and interpret what it means. 33 1/3, what does that mean? How many lots are made? Oh, the answer is that we can make 33 lots of this size with some land left over. So in the same way, I've given you a problem here that also makes use of fraction division. A cookie recipe requires 2/5 of a package of chocolate chips for each batch of cookies. If a restaurant has 20 packages of chocolate chips, how many batches of cookies can it make? So think about how that works as a division problem. Work it out, solve it, and interpret it. Take some time for that now. Welcome back. It may be surprising that you can take division problems that involve fractions and actually get a nice even number as an answer of 50 batches here. But indeed, that is possible, as you can see. We've seen how we multiply fractions. Now, how in the world do we multiply mixed numbers? Well, perhaps it's fairly easy to see how to do that by simply noticing that if we take 7½ and multiply that by 4 2/3, we can make the problem a lot easier by converting both of those mixed numbers into improper fractions. 7 1/2 becomes 15 halves. 4 2/3 becomes 14 thirds. And now it's very straightforward. It's familiar now. We know how to solve this multiplication problem. And in fact, you can actually see some things that can be canceled top and bottom. 15 and 3 becomes 5 and 1. 2 and 14 becomes 7 and 1. 5 over 1 times 7 over 1 becomes simply 35. In the same way, negative 12 times 1 7/9, well, negative 12 is just represented as negative 12 over 1, times, well, we have to convert this to an improper fraction again. That's 16/9. The parentheses are there. They don't really do anything, do they? Because they just encompass a single number, 16/9. So we don't really need them, but they're there anyway. And you can actually see, as we're doing this multiplication here, that there's some things that can cancel. 12 can be canceled with 9. 3 goes into both of those things. If we cancel out a factor of 3, that the 12 becomes a 4, and the 9 becomes a 3. We then multiply top and bottom to get 64 on top, 3 on the bottom. The answer is still negative because a negative times a positive is still a negative, and we can transform 64 thirds into negative 21 1/3. So in the same way, using the same technique of multiplying mixed numbers by converting them into improper fractions, do some practice for this with these next two problems. Welcome back. Hopefully this provided you with some additional practice working with multiplying mixed numbers. Dividing mixed numbers, it's the same procedure, except that instead of multiplying, we are, well, dividing. And so, once again, we are transforming these mixed numbers into improper fractions. 13 5/6 becomes 83/6, and dividing by -7 becomes multiplying by -1/7. So we're actually doing 2 steps there at once. Hopefully you're catching that. We multiply the tops and the bottoms to get negative 83 over 42, and that can be converted to a mixed number, negative 1 and 41/42. In the same way, on the second one, negative 6 divided by negative 5 and 1/7. Well, let's first of all take care of the negative signs. A negative times a negative equals a positive, so both of those negative signs can go away. And we will be converting this to multiplication, so let's just do the cancellation now. 6 can be converted to 6 over 1 divided by 36/7. That's 5 and 1/7 converted to an improper fraction. That then becomes 6 over 1 times 7/36, which you'll notice that there's a common factor, top and bottom, 6 and 36. The 6 cancels out, leaving a 6 on the bottom, so all we have is 7/6, or 1 and 1/6. I've given you 2 problems to do here for dividing mixed numbers. Welcome back. Again, a lot of cancellation takes place in both of these problems here. You can see canceling out factors of, on the top one, factors of 2, and then 2 again, and then 2 again, leaving us with negative 14/9, giving us a final answer of negative 1 and 5/9. On the second one, we're canceling out factors of 8, leaving us with just 1 and 2/3 as our answer.